Our reaction has a rate constant of 0.0224 per second at 298 Kelvin and 0.459 per second at 303 Kelvin. Determine the activation barrier for the reaction. Activation barrier is also known as activation energy. So to solve this problem, we will make use of the Arrhenius equation. So Arrhenius equation is ln K2 over K1 is equal to negative EA over R times quantity 1 over T2 minus 1 over T1. So let's define all the terms here. K2 is your rate constant at the second temperature. K1 is your rate constant at the first temperature. EA is the activation energy. R is the universal gas constant. T2 is the second temperature, and T1 is the first temperature. Since the question is asking us to solve for the activation energy EA, we need to rearrange the equation. So first thing, divide both sides by 1 over T2 minus 1 over T1. So this whole thing in parentheses will cancel. On the right side, you have 1 over T2 minus 1 over T1. So your equation would be negative EA over R. And on the left side, you have ln K2 over K1 divided by 1 over T2 minus 1 over T1. Then you need to multiply both sides of the equation with R. So times R on the right side, and on the left side, times R as well. So R will cancel on the right side, and on the left side, you have R times that whole thing. So your equation would be negative EA is equal to R times this whole thing. ln K2 over K1 divided by 1 over T2 minus 1 over T1. And to get rid of the negative sign beside EA, you need to divide both sides by negative 1. So divide this by negative 1 and divide this whole thing with negative 1. So the negative would cancel out. So finally, our formula for the activation energy, EA, is equal to negative R times ln K2 over K1 divided by 1 over T2 minus 1 over T1. So we will use this formula in solving for the activation energy. So let's start substituting the values. So activation energy is equal to negative R. What is the value of R? R is 8.314 joules per mole K. So you will not use the other R that we usually use in ideal gas equation. For Arrhenius equation, you will use the R with the unit joules per mole Kelvin. And then You multiply this with ln K2. So the rate constant at temperature 2 is 0.459 s raised to negative 1 divided by K1. The rate constant at temperature 1 is 0.0224 s negative 1. And for the denominator, we have 1 over T2. So the second temperature is 303 Kelvin minus 1 over T1. The first temperature is 298 Kelvin. So you just plug this whole thing in your calculator, and your activation energy EA is equal to 453,423.793, and the unit would be joules per mole. So if you check the units, S negative 1 would cancel, the Kelvin would cancel, and you're left with joules per mole. So the answer is quite a big number. So one way to conveniently express your answer is to have the units kilojoules per mole. So in order to convert joules per mole to kilojoules per mole, you just divide your answer by 1,000. So this whole thing divided by 1,000 would be equal to 453.423793 kilojoules per mole, or approximately equal to 453 kilojoules per mole. So this will be your answer to the question.